Hi guys, welcome to the rest of the semester. Not sure if I'll see any of you in person this semester, but I will be providing instruction as much as possible via Blackboard to get you through. I don't really have to assign incompletes to any of you. As I stated in my email, it's up to you to do the work assigned. You have an opportunity to complete this course, not a guarantee. I'll be creating videos each week covering the lab objectives for that week. Your job, watch the videos, write a report each week to demonstrate that you've watched and understood the material that was demonstrated. The report must be submitted by email each week. To get credit for the lab, your report must be 2 pages long, normal size font, not a 48 where you got 2 words per page, no bigger than 12 for the font size. Normal margins like 1 inch. Included in the report should be a detailed description of what you watched, any measurements taken, the numbers associated with those measurements, the results of those measurements. Were they normal? What conclusions can be drawn from the results? Include the recommended repair or replacement that would fix the problems we worked on. So up to now we've been doing all inputs. At this point in the semester we need to start discussing computer outputs such as relays, solenoids, motors, displays. Some of the demonstrations will be done on the bench, others will be vehicles out in the shop. Unfortunately, we will have no live problems to diagnose. So we'll start with relays and see where it goes from there. In our first discussion here, we're going to talk about relay control of devices, indirect control. So the first thing I want to show you, right here, I have a little electric motor that came out of that actually causes the seat to vibrate when the vehicle crosses over the double yellow line or crosses over a line on the street to warn the driver. It's the lane departure warning, and it's just a little tiny motor. And what I'm going to do is I'm going to hook this up. So you notice I have the meter here. I'm going to set the meter on DC amps, and of course we put the leads in the 10 amp right here, 10 amp spot, and then I'm going to run my power from my little power supply through this meter and into this little electric motor, and then from the motor back to ground. And well, let me turn this off a second. So this motor is meant to vibrate and alert the driver when you when you go out of the lane when you're not supposed to. So if we look at the amps, it's about 1/4 of an amp, 0.27 amps. Let me shut that down. It's kind of hard to hold on to. If I take this motor and substitute this power window motor in its place, we're going to find it's probably a bit higher. Take a look. It's a little over 4 amps, and that's with no window load on it. So this is just the motor spinning by itself, maybe 3.5 amps. So how do we deal with this? If we're trying to control this big motor with a computer's not going to be able to handle that 3.5, 4 amps. And you know it's going to be higher when there's actually a window attached to this motor and that extra load on it. So that's where a relay comes into place. So let me move this motor out for a minute. And here I have a 5-pin relay. So when you look at this, over on this side is the relay coil. This is what's going to be the electromagnet inside the relay that's going to control the switch on this side, on the load side of it. So 5-pin relay, when it's not energized, there's a connection between, this would be pin 30, this would be pin 87A. When it is energized, that connection moves off of 87A and over to 87. So whatever was on here would turn off, and whatever's off here would turn on. So if I just hook this little power supply to the relay, you may be able to hear it click. I'm not sure how it's going to come across on the camera. Here we're going to see just how much current it takes to energize this relay coil. So I'm going to run current through this side of the relay, the coil side, but I'm going to run it through the ammeter on the way there and see how much that takes. So we're going to run from my power supply to the ammeter, from the ammeter then to the coil, and of course the coil has a ground on the other side here. So when I turn this on, it's 0.19 amps DC to energize that relay coil. So if you remember, the tiny little motor here was a fairly small amount of current. The big old power window motor was several amps of current. So the question is, can we somehow power this power window motor without running a lot of current on the control side? So this control side is what would be operated by a computer. You push a power window switch, you're telling the computer, I want the window to go down. It needs to energize that window motor, but it can't handle 3.5, 4 amps of current flowing through it. So what's going to happen instead is the computer is going to energize the relay coil, and as you saw, that's only not even 0.2 amps, so a fairly small amount of current. Now why would that be? So that's one of the questions you have to answer. Why such a small amount of current in that relay coil? What keeps the current flow down to a low level like that? So let me unhook this, and we'll get the ammeter out of here a minute and just see how the relay can be used to control something, pretty much anything. So I have here a light bulb, and I'm just going to hook the light bulb to the output side of the relay, the load side of the relay, and to ground. And I will provide power to the load side of the relay. So theoretically now, when the relay kicks on, which I don't know if you'll be able to hear it or not, we should get light from our light bulb. So let me get that where you can see it. All right. Energize the coil. The switch inside the relay flips, sends power to the light bulb. When the coil is de-energized, a spring flips that switch back, and the light bulb is now de-energized. So the light bulb doesn't take that much current. What about that power window motor? Let's plug that in place of that light bulb. So now, you remember this power window motor took a lot of current. But if we operate it with the relay, how much current are we using on our control side? So you know the relay coil only takes 0.18 amps to operate, but by using that 0.18 amps to energize the relay, when the relay closes, the contacts inside the relay on the load side provide current to the window motor, which is taking, we know, between 3.5 and 4 amps, and that's without a window on it. So this is called indirect control. This is how a computer can send a small amount of current through the relay coil and control a much larger amount of current, like through this motor. What have we learned so far? One thing we've learned is that there's two ways that motors can be controlled by a computer. There's direct control. Now the problem with direct control is all of the motor's current is running through the computer circuitry, which is small and delicate, so it can't handle a whole lot of current flow. A little motor like this, maybe. This was, what, 1/4 of an amp? I don't remember. That's something you got to put in your report. When you watch this video, write down numbers. So that can be controlled directly, small current flow. This motor, no way. This was 3.5, 4 amps. You try to control this directly through a computer, the circuitry inside the computer is too small to handle this kind of current flow. When this motor has a load on it, like when it's trying to pick a window up or down, it's going to be way more than 3.5 or 4 amps. So how does a computer control something like this? We have this go-between, this relay. And what the relay does, the relay, if you remember, was about 0.18 amps to operate the relay. Can the computer put out 0.18 amps? Yes, it can. So by putting out 0.18 amps, closes the relay then supplies the current to the motor, and so we're using a small amount of current to control a large amount of current, and that's indirect control, and it's very, very common. This is how your fuel pump is operated. This is how any electric motor pretty much that's, except for the tiniest ones, are operated. Your electronic throttle control, those are generally direct control. But something like wipers, fuel pump, windows, those are heavy duty loads, and those are always done using relays or indirect control. Let me show you another application where a computer is directly controlling a motor. You're all familiar, most vehicles now use electronic throttle control instead of having some sort of a cable or a linkage. So give me a minute, I'll set this up and I'll show you. So what I've rigged up here, I have an electronically controlled throttle. I have 2 wires hooked right to the motor connections. And then I've rigged up a switch here that allows me to turn the power on and off to it easily. And then I've hooked that up to my power supply here that you guys are used to seeing in class. So the way I have it hooked up right now, when I turn this switch on, when I close it, hard to tell, but if you look closely at the throttle plate here, what's happening is it's actually closing when I power it up. So with no power to it, the throttle's in this kind of default partially open position. And when I close it, it actually puts it fully closed when I turn the switch on. If I turn these wires around the other way, so I'm just going to unhook my positive and negative and swap them. This will be a little easier to see. When I turn the switch on, you see the throttle goes fully open. So the way the computer does this, if it wants to close it, it applies power in one direction. If it wants to open it, it applies power in the opposite direction. To hold it in a fixed position, it needs to turn that power rapidly on and off to control the amount of current through that motor. And what it's doing is it's working against a spring. So as soon as I turn the power off, here we're wide open. When I turn the power off, or if I just pull the plugs right off of it, it's spring-loaded back to almost shut. Okay, as you can see, now we're out in the shop, and we have a Crown Vic with a cooling fan problem. First, we'll look at all data and see the way it's supposed to work, and then we'll do some tech checks on the car and see what's wrong. This is the wiring diagram for the cooling fan. What I'm looking at is the cooling fan relay, and you notice it is controlled by the PCM. So that's what makes this a computer-assisted mechanism. 2 sides to the relay. You've got the control side. This is pin 85, pin 86. Pin 86 has power supplied to it. in start or run. Pin 85 is the side that's grounded by the PCM. So when the PCM wants to turn the cooling fan on, it provides a ground on this red and orange wire right here. Pin 85 on the relay, pin 28 at the PCM. When that happens, the electromagnet in the relay pulls the switch contacts closed, connecting pin 30 to pin 87 in the cooling fan relay, sending power out this dark blue wire to the fan motor itself. So what we're going to do is we're going to do a few checks, make sure we have power where we're supposed to, make sure it grounds when it's supposed to, and then make sure that the fan runs when we send power to it directly. So the first thing I want to do is bring up a picture of the junction box where this relay is and make sure we identify all the different parts. So the first thing we'll do is find this relay box. So here's the battery junction box, and if we look down here, cooling fan relay is relay number 3. So right here. So relay number 3, there's 4 relays across. That's going to be this one right here, obviously. Third one in line. Also pay attention to number 17 here. Number 17 is a circuit breaker, which I'll show you on the car, that provides power to this relay. If I go back to the wiring diagram, that's this number 17 right here, 30 amp circuit breaker. So what we'll do is we'll make sure that we have power at this pin and at this pin. That's where we'll start, and then we can use a scan tool to try to ground this pin. So now here we are under the hood. Here's the battery junction box right here, and here are the 4 relays. We want number 3, and looking at this box we're counting across 1, 2, number 3 right there. I'm going to pull that out. As far as that number 17 circuit breaker, it's this big 30 amp circuit breaker right here. Get a better look at that. That is not easy to get out. So, I don't know if you can see it, it says 30 amp at the top. Similar to a maxi fuse, but it's an actual circuit breaker, so it will reset. So what we want to do is, I've got a test light here. I've turned the key on. These pins, looking at the bottom, number 30 is here closest to you. That one definitely lights. And number 86 is to the left. Oh, to the right, I'm sorry. And that one definitely lights. So we have power where we're supposed to on those 2 pins. So another thing we can check is if I hook my test light to battery positive, we'll see if pin 85 is a ground. It's not now, but it shouldn't be. The only time this should be a ground is if we energize this with the scan tool, letting the PCM create the ground. So that's what I'm going to do next. Okay, right now I'm hooked to battery positive with my test light. I am in pin 85 on the scan tool, which goes to the PCM. If the PCM creates a ground, that light should light. I have the Autel scan tool hooked up, and I'm going to turn on the cooling fan. Okay, so the light lit, telling me the PCM is capable of creating a ground on that circuit. Now we'll turn it off. Take this out. So now we've verified that we have power on pin 30, we have power on pin 86, and we are getting a ground on pin 85. So one last thing we can check, is the fan motor itself and the circuit to it any good? So what I'm going to do is take a jumper wire, hook it into pin 30 and directly to pin 87. And I don't know if you can hear that, but I can hear the fan motor is running. So that tells me, the wire's getting a little warm too, that tells me that the fan motor is good and that the wiring to the fan motor and the ground is good. Okay, so where does this leave us? Let's see what we just did. We checked the number 17 30 amp circuit breaker. We never really looked at the circuit breaker itself, but we checked where that power goes into the relay here, pin 30 of the relay, and we had power there. That tells me everything up this line is working the way it's supposed to. Next thing we did, we checked pin 86 here. It says 12 volts. I don't know if you can read that, but that's what's supposed to be there. We checked, we had 12 volts there, so we can forget everything up this line. It's all fine. Next, we wanted to know, is the PCM, let me adjust this a little bit. Is the PCM able to ground this red and orange wire here? So I hooked my test light to battery positive, stuck it in pin 85 here, and when I activated this relay with the scan tool, causing the PCM to create a ground on that wire, our test light lit. That tells me this wire is good, the PCM is capable of controlling it, the problem is not here. So that left us to check the output of the relay. This dark blue wire goes right to the cooling fan motor. One way I could have done that is I could have ohm meter checked it, but instead I took a jumper wire and in place of the relay I put the jumper wire right across from this hot wire from the 30 amp circuit breaker directly to the wire that goes down to the fan motor. The fan motor kicked on. That tells me this wire's good and the fan motor's good and the ground. So here's for your report. What does that leave? What is the problem with this cooling fan circuit? Write it down. That concludes our discussion about relays and indirect control. You saw earlier on the bench, we controlled the power window motor indirectly through a relay. Then we controlled an electronic throttle directly, no relay involved. The little seat vibrator motor, that was controlled directly. Out here, the cooling fan motor, you can see since it's a heavier current load, that's controlled through a relay. We did a diagnosis on a theoretically inoperative cooling fan motor, and we verified all kinds of wiring, and we verified the voltage we needed at different places, or at least power, and we verified the grounds and the operation of the motor itself. So I'll give you a little bit more detail on how to write this up, but that's going to be your grade for the lab, is watching all of this, writing it up. Next week we'll do something else.